Hello! Today we're going to be studying energy transformations. This picture shows an energy transformation from the sun to riding a bike. You're probably thinking, my bike isn't solar powered, my bike doesn't run on sunlight, but it does and I'm going to prove it. It's just that we need to go through several steps to get from the sun to the bicycle. Well, the sun is nuclear powered. It uses nuclear fusion to produce the sunlight and the intense heat. Well, that sunlight or radiant energy hits the plants. So we have some plants growing in the field down here. Plants have this special thing they can do called photosynthesis, where they convert that light or radiant energy into chemical energy, and they become food for us. So the food goes to the grocery store, and this boy ends up eating the salad. Well, when he eats that salad, his body converts the chemical energy in the food into kinetic energy so that he can move and he can pedal his bicycle. Now, his body also turns some of that food into thermal energy. So you'll see thermal energy is just kind of going out. Think about your body heat. Your body temperature is always around 97 or 98, somewhere close to that, all the time. In the summer, in the winter, unless you're sick, that's your normal body temperature. And your body maintains that temperature by burning some of that chemical energy in the food that we eat. So the thermal energy is kind of a waste there, but your body can power your muscles to pedal the bike using the chemical energy in the food. And finally, we have mechanical energy in the bicycle. So there's a lot of energy transformations there, but ultimately we can trace the energy to pedal that bicycle all the way back to the sun. We have this thing called the law of conservation of energy that says energy cannot be created or destroyed, but it can be transformed from one form of energy to another. For example, we talked about photosynthesis. Plants use sunlight to turn it into chemical energy in this carrot. All food has chemical energy, and then it can be transformed to the mechanical energy in the bicycle. A stove might use electricity or electrical energy to get hot and heat up whatever's in this pot. We call heat energy thermal energy. Chemical energy is also in things like gasoline, firewood, anything we can burn. Remember, chemical energy is stored in the chemical bonds between the molecules or compounds. So the car actually burns the gasoline, releasing that chemical energy and turning it into mechanical energy in the car. Now notice down here at the bottom it says something interesting. In every energy transformation, some energy always gets converted to thermal energy. We talked about how when you eat food, your body produces some body heat, thermal energy. Well, think about a car that's been running for a long time. If you were to feel the hood, put your hand right there, it's going to be hot. In fact, your car has to have systems to get rid of that heat. Your car has water pumps and fans and radiators, all to get rid of that thermal or heat energy. If you don't get rid of that energy, the car can overheat and break down. So there's always going to be some thermal energy. Even think about the sunlight and photosynthesis turning to chemical energy in the plant. Well, when you stand outside on a sunny day, you don't just see the sunlight. You also feel the sun's heat or thermal energy. Even the person who is pedaling the bike, you know that if you work really hard and exercise, you get hot as your body produces more thermal energy. Let's look at some energy transformations in a flashlight. What powers your flashlight? Well, must have batteries in it. So we have some different energy transformations. Let's look at what form of energy is in three different spots. In the battery itself, coming out of the battery and running through the wires, and then actually in the light bulb. What kind of energy do you think is in the battery? Think about it. I'll give you a hint. It's a form of potential energy stored in the chemicals that are inside. Batteries have a lot of very strong chemicals, particularly acids in them. Hopefully you guessed chemical energy. So there's chemical energy in the chemicals inside the battery. Well, chemical energy is a form of potential energy. It's stored energy. It doesn't become kinetic energy or moving energy until you actually turn the flashlight on. And then we have a form of kinetic energy that runs through the wires. Electrons move through these wires. Does anybody remember what form of energy involves moving electrons? If you guessed electrical energy, you are right. So the chemical energy in the battery transforms to electrical energy when you turn it on and electrons start moving through the wires. Those electrons in your electrical energy eventually get to the light bulb and the flashlight. And we have another energy transformation that happens. In fact, our electrical energy transforms into two different types of energy. The one would be radiant. Radiant's just a fancy name for light. That's the whole point of a light bulb. But there's also a fair amount of thermal energy. Light bulbs get hot. And again, in every energy transformation, there's a little thermal energy. But light bulbs actually waste a lot of energy as thermal. We really want it to light up, but it's going to get hot too, and that's a waste. All right, let's take a look at a different example. Potential energy can be converted into kinetic, and kinetic can be transformed back into potential energy. We often call this mechanical energy. Remember, mechanical energy is the sum, the total, when you add all the kinetic and all the potential energy together. Here's an example of that we saw in class. So we have our ski jumper, and it asked you to add up the mechanical energy at every point. Well, at point A, look, she has no kinetic energy because she's not moving. She's just waiting to start her ski jump. But her potential, because she's very high off the ground, she has a lot of potential for gravity to pull her down, is 50,000 joules. What's 0 plus 50,000? You should have said 50,000 joules. She has 50,000 joules of mechanical energy, or total energy here. Now we're going to have an energy transformation happening. So when she gets right here, she's about halfway down that first hill. Notice how she has some kinetic energy. She's starting to move fairly fast. The faster you are, the more kinetic energy. But she still has a lot of potential energy too, because she's only halfway down the first hill and there's still more hills coming. So she's got the potential to keep going down. Gravity will pull her down. If you add those, 20,000 plus 30,000, what do you get? Oh, look, it's 50,000 joules again. If I were to add up her energy, actually, I think I was supposed, no, that's right. If I were to add up her energy at point C, here we are at the bottom of the hill. If I add up her energy there, 50,000 kinetic energy, because she's going to be moving really fast by the time she gets to the bottom. But notice her potential energy is 0. She doesn't have the potential for gravity to pull her down. She's on the ground. You can't go down any farther than that, unless a giant hole opens up. But notice when I add those, I get 50,000 again. What did you notice? Mechanical energy is the same everywhere. So her potential energy here gets converted to kinetic energy and still some potential, but by the bottom it's all converted from potential to kinetic energy. She has no more potential energy, it's all kinetic. At the beginning it was all potential. Sometimes it's more like half and half. All right, let's give you a chance to try some energy conversions or energy transformations. You're going to see some examples on the next slide, and you're going to decide what sort of energy transformations are happening. Now, you do need to remember your forms of energy. For example, if you're staring at a battery thinking, I have no idea what kind of energy that is, you may want to go back and do the lesson earlier this week, the sway on forms of energy. Otherwise, go ahead and move on, and good luck.